Okay, this is a lesson to help us understand a little bit more about friction and how exactly it's calculated. First of all, friction is something that occurs when we have two surfaces in contact. So the two surfaces have to be going against each other. And even if the surfaces feel really smooth to our fingers, at the microscopic level, it would look more like what you see in this picture right here, where the two surfaces, even if they feel smooth to us, would be very jagged. And it's those two surfaces, kind of those peaks and valleys hitting each other, that causes friction. There's also an electromagnetic force that's called a bonding, called cold welding. So when things are put together on top of each other, they adhere to each other because of protons and electrons, essentially. And in order to get the two objects to separate, you actually have to break those cold welding bonds. So that's another thing that goes along with friction as well. And generally for us, the direction of friction is that it opposes the applied force. That's not always the case, but for the simple problems that we're doing, that will generally be the direction of the friction. So one thing we're going to see today is what things does friction depend on and what doesn't it depend on. So by the end of class, we'll be able to figure this out. Perhaps it depends on the weight of the objects, or maybe it depends on the surfaces, or how fast the objects are moving, or the surface area. So we're going to figure out what is the answer to that. But first, we need to know that there are two types of friction. The first type is when we push an object and it doesn't actually move anywhere. So, I could be pushing on a desk or something like that, and I'm trying to move the table, and I'm pushing, but it's not actually going anywhere. That is called static friction. And the symbol for that is going to be F sub S, is usually what we use there. And once it starts moving, that is going to be called kinetic friction. So if I am pushing on the object and it finally starts sliding, then you're looking at kinetic friction, which is F sub K. And the question is, which one of those is bigger? And so if you imagine sometime when you've pushed maybe a heavy piece of furniture, think to yourself, what was harder to get to happen? Was it harder to get the heavy piece of furniture to move in the first place? Or once it was moving, was that harder? And I think if you think back to your experience, you'll realize it was harder to get the thing to start moving than it was to keep moving. And that's because the maximum, and you'll understand this a bit more in a second, the maximum static friction is always going to be greater than the kinetic. So it's harder to start moving than it is to just keep the object moving once it is moving. Right. So we need a number in order to be able to describe the surfaces in contact, because of course it's totally different if we have a wood piece of furniture that we're trying to slide across a wood floor. Are we trying to slide it across carpet? Are we trying to slide it across like a glass surface or ice or something like that? So it really matters what surfaces we're talking about. So we need a number for that, and the number we're going to use is this Greek letter, and it's pronounced mu. You've seen that before in terms of micro, meaning 10 to the negative 6. This is a different use of that. But it's called mu, and it's called the coefficient of friction. And what this is, it's a number that's based on the surfaces in contact. And both surfaces matter, certainly not just one, but the combination of surfaces, it's what's important. So the formula we have to calculate friction, so this in general right here is the force of friction. And what you're going to do is take the coefficient mu, and it'll depend on what the surfaces are, what number you're going to pick. This will make more sense in a moment. And you also have to decide, is it static or kinetic? So if it's static, you'll be using a little bit bigger number. If it's kinetic, it'll be a little bit smaller, but that's the number that goes there. And then this represents the normal force. Sometimes I write that with just a lowercase n, but that's the normal force. So you're going to take the coefficient of friction times the normal force, and that will give you the size of friction. So we need to know the units of mu. Well, if you get the mu by itself, it's equal to the force of friction divided by the normal force. those are both measured in newtons. Anything over itself cancel, so there are no units for the coefficient of friction, which makes sense. That's why it's called a coefficient. A coefficient means it's just a number in front, and that's what this is. Mu is just a number in front of the normal force. All right, we'll get some examples in a bit where you'll see us actually using this. But first, I want to show you some examples of different coefficients of friction. So here you see a bunch of different combinations, like wood going across wood, or maybe you have rubber on concrete. And you can see this column is the static column, and this column is the kinetic column. So if I had a case where I had a wood piece of furniture and I'm trying to get it to slide on a wood floor, this is the number that I would use. If it's already sliding, then this is the number that I would use. And notice as you go down these columns, it's always greater than for the static than the kinetic. So this number is always bigger than the other one because, again, it's harder to get it to move than it is to start moving. Right, now before we get into the equation a little bit more, there's an important graph I want to make. So on this axis, we're going to graph how much friction there is. So we're graphing the friction force. And on this axis, we're going to graph my applied force. So imagine I have an object here. Of course, it has a weight. It has a normal force. And let's imagine that it's a desk that I'm trying to move in the classroom. And first, I'm just going to push on it very gently. So like with my finger, barely pushing at all. So really, really small. So that would be my applied force, really, really small. And if it's not moving, it's got to be in equilibrium. So that means the frictional force would also be really, really small. So if I plot that point, it would be here. My small frictional force is matching my small applied force. Now, if I push a little bit harder, maybe I'm pushing with my hand a little bit harder, well, it's still got to be balanced because it's still not moving yet. I haven't pushed hard enough. So my static friction number has now grown. I'm pushing harder, so friction is balancing bigger. And so now there is my new friction value. And you can imagine I could keep increasing my push, and friction's going to keep matching that up until a certain point. So this graph right here represents the static region of the graph. And static friction can be any of these numbers leading up to this point right here. What's important about this point is that this is the maximum static friction. That's equal to basically the most static friction possible. So if I want to get the object to move, I'm going to have to push a little bit harder than that so that it can no longer balance out and the object will start to move. Now, this is also what you get when you do mu times the normal force and you're using the static value. It doesn't calculate any of these other numbers, it only calculates the maximum possible answer. We'll see some examples of this later on. Okay, well then what's going to happen is the object is going to start to slide. And once it starts to slide, something interesting happens with the friction value. This is what the graph looks like. Notice, first of all, it dips down. So this is my kinetic friction. So first of all, it's lower than the static friction. But second of all, it's a horizontal line. And that's because kinetic friction is constant once the object is moving. Meaning it's not going to be bigger if you push harder or less or whatever. As long as it's moving, that number is going to stay the same. Okay? So it doesn't change if accelerating or constant velocity or decelerating, if it's slowing down, it doesn't matter. Once it's moving, kinetic friction is going to be a constant arrow, and regardless of what you do over here, once it's moving, that kinetic friction number is not going to be changing. It's going to be equal to whatever that number is right there. So this is your kinetic friction, this is your maximum static friction number. Okay, let's look at a quick example here. We want to move a 120 kilogram wooden piece of furniture across a wood floor. So we're going to find both maximum static friction and kinetic friction. Again, because we're talking about wood going across wood, we're looking here. This is the number that I use to find that static friction. And this is what I use to find the kinetic. But first of all, I know that it's a 120 kilogram piece of furniture. So this is going to be 1,200 newtons. I took 120 times 10 to get that, because weight is mg. Well, if it's on a flat surface, the normal force would also be 1,200 newtons. Those are going to balance. So now what I want to do is find the maximum static friction. So you take mu times the normal force. For static friction, the number would be 0.4. And I multiply that by the normal force, which is 1,200. And we multiply that and we get an answer of about 480 newtons. So when I am trying to get this thing to move, I'm going to have to push with at least 480 newtons in order to get the object to move. Now, if I'm asked to calculate kinetic friction, once it's moving, well, the only difference is now I'm going to use the kinetic friction number, which is 0.2 instead. So I'm going to take 0.2 times 1,200, and that's going to be 240 newtons. So once it's moving, that's the only friction that's going to be left. And you can see it's literally half as big. So once that piece of furniture is moving, the friction has declined considerably, and it's half of what it used to be. Okay, last question. Let's imagine a 10 Newton force is applied to the side of a 4 kilogram block sitting on a table. It experiences a frictional force. So this is just going to kind of walk us through the whole problem. First, we're going to draw the diagram. So I know that it has a weight pointing down. I know there's going to be a normal force balancing that. You can call it either F sub n or just n. I'm going to be applying a force. So this is my applied force. And I know that there's going to be some friction opposing that. Depending whether it's moving or not, that will decide if it's static or kinetic. So B is asking what's the weight of the block. Well, if it's 4 kilograms, weight is mg. So the weight is going to be 40 newtons. Then it says, what's the normal force? Well, it's not accelerating up or down. This is a flat surface. So your normal force is also 40 newtons. Now it tells me that I'm pushing with a 10 Newton force. So this is 10. Letter D says if the coefficient of kinetic friction is 0.2, what is the frictional force? Well, to calculate friction, it says it's kinetic, so it's moving. You do the kinetic friction times the normal force. So the kinetic friction coefficient is 0.2, and you multiply that by the normal force, which is 40. So we're going to go ahead and do 0.2 times 40, and you're going to get 8 newtons. So that's how big friction is. Right? So this block is sliding, and I can see now it is not in equilibrium. The applied force is bigger than the frictional force by 2 newtons. So the net force is 2 newtons. I can just look at my picture. And now we can go back to Newton's second law, and I can do net force equals ma. I know that the net force is 2 because that's how unbalanced it is. I know that the mass is 4 kilograms, and I can simply divide to get the acceleration. And the acceleration would be to the right, since the right side is bigger than the left. And since I'm pushing it to the right, that would also mean that it is in fact speeding up.